Okay, so this is section 7.5 titled Work, and the first definition we have here is work done by a constant force. If an object is moved in a distance d in the direction of an applied constant force F, then the work W done by the force is defined as W equals F times d. So in this first example, we see that we have a 50-pound weight moving 4 feet. So work is equal to 50 times 4, which is 200 foot-pounds. Again, 50 was in pounds and 4 was in feet, and those two labels come together as foot-pounds. So this example didn't need calculus. This is a simple example. There's not a changing weight or a changing volume or a changing density, so it's a simple formula that we plug into. But if we look at an example like Hooke's law, where we have changing forces, that's where calculus is needed. So we have our definition of work done by a variable force. It says if an object is moved along a straight line by a continuously varying force f of x, then the work W done by the force as the object is moved from x equals a to x equals b. And we can write this as work is equal to the integral from a to b of f of x dx, where f of x is equal to the force function. So the force function is what we have to develop from applications, reading them and interpreting them. And if we read Hooke's law, we see that the force F required to compress or stretch a spring within its elastic limits is proportional to the distance d that the spring is compressed or stretched from its original length. And that is to say that F is equal to K times D. And in this, we say that K is the spring constant. The spring constant is a result of the design of the spring, whether it's a coil spring or if it's some other type of a spring like a leaf spring. It's also a result of what the spring is made of, steel, rubber, something that has elasticity to it and being used as a spring. So that's what contributes to the spring constant. And then D is the displacement of the spring from its equilibrium. So if we look at this example number 2, it says that a force of 750 pounds. So 750 pounds is our force. And a force of 750 pounds compresses a spring 3 inches. That's our D. So we have enough information to solve for K. Divide both sides by 3, and we get that the spring constant in this example is 250. We can now write our f of x, our force function, is equal to K, which is 250, times x, which is our displacement. So we're going to use x as the variable for changing displacement. And now all of this can be put together. Work is equal to the integral of 250x dx see if I can make that more legible. And now we have to figure out the bounds of integration. So if we go back to the problem, it says find the work done by compressing the spring an additional 3 inches. The spring is already compressed 3 inches, so it's starting from a 3-inch displacement, and 3 additional inches would be up to a 6-inch displacement. So we've set up the integral. Now we just have to apply the power rule and then the fundamental theorem of calculus. And when you solve this problem, you should find that you get a answer of 3,375 inch-pounds. Again, because now we're dealing with inches and pounds, our label is inch-pounds. So that's 3,375 inch-pounds. And I leave the work for you to do because it's simple power rule. So here's the big problem we want to work on here. This one doesn't have any standard equation, but we're going to derive the force function by reasoning with the problem. So it says that we have a spherical tank of radius 8 feet. It is half full of oil, and the oil weighs 50 pounds per cubic foot. Find the work required to pump the oil out through a hole in the top of the tank. So if we look at this, we have layers of oil, and each layer of oil is delta Y. And we're going to be pumping the oil out a hole in the top, which is moving vertically along the y-axis. So from all of that, we should come to the expectation of writing this integral as a function of y. Great. So now we have to say, well, what shape is each of these layers of oil? And they should look like discs, right? So each disk, we want to be able to calculate its volume. So if I have a disk of oil here, I need to find the radius of that disk. And we say, well, since this is a spherical tank, I can plot this on a coordinate plane. It says that the spherical tank has a radius of 8 feet. So we know that the coordinates, if we center this at the origin, are going to go from -8 to 8 on the x and the y axis. That means we have x squared plus y squared equals 8 squared. That's our equation for the circle. But we don't need the whole circle. We just need the distance from the center to the side of the circle, because each of these are going to have a radius. See this disk? So this radius is the distance from the center to the side of the circle, from the center to the side of the circle. So that means we want to find the equation for just the right-hand side of the circle. It has to be a function of y. So we're going to write this as x squared equals 64 minus y squared. X is equal to the square root of 64 minus y squared. We want the positive square root because we're using the right-hand side of the circle. Great, that's the radius. But now I need to find the volume of this disk. So the volume of the disk is equal to pi times the radius, which is the square root of 64 minus y squared. So pi r squared, we square that radical, times the height, which is delta y, and that's the volume of the disk. So now I can start to say, all right, the work is going to be, they said it was 50 pounds per cubic foot. The integral, I haven't gotten the bounds yet. We'll get to that. We have a pi, I'll put outside since that's a constant. And the 64 minus y squared and the square root squared, that'll come out of the radical, the 64 minus y squared. And so far we have just the disks. Now we have to have the distance that each disk has to travel. So let's go back up to our image. How far does each disk have to travel to get out the top of the oil tank? So it says that the oil tank is half full. So this is all of our oil down here. And when I have oil at the bottom of the tank, it's at y equals -8, and it needs to travel to the top. And the top is at y equals 8. So to get it out the top, it's going to have to travel 16 feet. So we have an -8 as the position of the oil. And 16 as the distance it has to travel. And then if I go to the middle of the tank, where it's half full, we're at 0 for the y coordinate. And when the oil is at the 0 coordinate, it has to travel 8 feet to get out the top. So those are our 2 points. We will write a linear function that follows that path out the top. So when you do this, you should find that the distance that as a function of y is going to be 8 minus y. So this is part of the force function. We want to go back down to our integral, and we say, great, the force function consists of 2 things. It consists of the volume of each layer, and then it consists of the distance that each layer has to travel. So there we go. So the volume and the distance. Now we just need the bounds of integration. If we go back to our drawing, we're going to be pumping oil from -8 to 0. So those are the bounds that we want to use. And now you would FOIL these 2 together and then use your power rule to integrate. And when you complete this problem, you should find that you get 500. This pen is not cooperating. So 589,782 foot-pounds. And that's the example with the pumping oil out of a spherical tank.